So warm greetings everyone who has joined this session. My name is Sargun Kohli, and on behalf of entire HTS team, I'm glad that all of you joined this session, which is on the topic Data Analysis Methods of Future by our chief guest, Dr. Paul R. Yarnold. And I'm assuming most of you must be knowing about them already if you've attended a previous session of Research One-on-One, and it's an honor for us to have him as a guest again. So to talk about the flow of this event, in a matter of few moments, we'll be starting with this event, and this event would be done by our guest. And then all of you will be given a chance to get all of your questions and queries resolved in the Q&A session. Then this will be followed by a thank you note by the event organizer of HTS. Moving on, I'd like to take this opportunity to introduce you all to HTS. It's a completely student-driven technical society of Chandigarh University. Hackoverflow Technical Society has conducted many webinars and illuminating sessions, including Google Hashcode 2021, where we successfully managed to secure 7th position globally. We conduct many webinars and sessions ranging from global level hackathons to interdepartmental level competition sessions, webinars, and much more. So to talk about a speaker of the day, Dr. Paul R. Yarnold. He's an internationally acclaimed researcher. He's also the director of optimal data analysis, and his passionate dedication has made him the author of 6 books, out of which 2 of them are bestsellers. Over the time, he has written over 632 journal articles and has around 23,000 citations. In addition to all of this, he was also offered by Steve Jobs to join his team while he was preparing and designing his first mouse for Mac. So it's an honor for us to have you as a guest today. I'd now like to invite and request Mr. Pawan Kumar, Additional Director, Apex Institute of Technology of Chandigarh University, to welcome the guest. So please, if you're here.
I believe, Sargun, that sir will join us at 7:35. Can you move to the previous?
Yeah, I'm there. If you can hear me.
So please.
Am I audible?
Yes, sir, you are audible.
Yeah. Hello. Good evening, everyone. Good morning, Dr. Paul. I believe it's morning there. Yeah. So it's indeed a very proud moment for me to welcome you on this session. And indeed, if you have spared time to be with us and share your knowledge, your insights, and your experience, it's really a privilege for my institute and my students to be listening to you in this evening in India. Data analysis is it's not a option for any professional in this world. It is a necessity now. You cannot survive if you are poor at handling and analyzing data, because data is what is called lifeline of everything we do, pretty much everything we do in terms of our workplaces and our governance and our life. And in last 5 years, we have probably seen the avalanche of data in all forms, right? We are not only generating data in every moment of our activity, but we are also being driven and controlled by data with various tools which are there. So for students who are aspiring to have a successful career journey, who are aspiring to pick up skills which would take them through their 20, 30, 40 years of career ahead, data analysis definitely is among the top. So, and when we are talking about data analysis methods of future, it means it's no longer static analysis, which we used to do, for a few decades till now, but it's much more complex and much more dynamic, going forward. So, Dr. Paul, we really look forward to, learning and getting to know more about how data is shaping our lives and how data analysis methods would eventually play out in terms of decisions we take in our workplaces and in our society. I warmly welcome you on behalf of the Chandigarh University and Hackoverflow Technical Society. Just to share with you, HTS is one of the most active society of our institute, and the students are among the most active and passionate, who are driven by their quest for knowledge and zeal to learn more and more. And it's entirely student-driven society. This event, what we are all gathered here for, is entirely an initiative and organized by this society. So my heartiest congratulations to entire team of HTS for putting it together and bringing us on this platform. And I really hope that the students who are joining us in this evening to listen to Dr. Paul would definitely and immensely benefit from his words of wisdom and his expertise in data analysis. So with this note, I welcome you for your session, Dr. Paul.
Thank you very much. It's an honor to be here because honorable people have invited me. It is symbiotic. It only works in that direction. So thank you very much. Namaste. I grieve for the tribulations of India in this pandemic and pray for the speedy and complete resolution of this. It is a great privilege and honor to speak to the Hackover Technical Society about my life's work. The subject today represents approximately 70 standard man-years of effort. I usually worked at least 2 shifts a day, at least 6.5 days a week. I especially wish to thank Danish and Dr. Chebrolu for making this possible, as well as all of you. Let me say, in relation to the comments that we just heard, that it took me 10 years of serious work as a graduate student and as a young professor to understand what was going on in the world of statistics. I took Einstein's model. Einstein said that he had to read everything that was known in his area of research so he could figure out what the problems and the questions were. And then he went ahead and made his discoveries. I had to do the same thing. So let me tell you, if you're gifted, that means, well, I'm going to go to the first talk and that's where I say what gifted is. If you like statistics and you do well at it, it will probably take you about 10 years to figure out what everybody has done. Okay, if you decide instead to learn what I am talking about, it will take you 1 to 2 years. Okay, and you'll see what this talk will show you what you'll get out of it. However, the most important thing for every scientist and every administrator and every manager is measurement. If you are trying to track something and you measure it imprecisely or incorrectly, you're fooling only yourself and everybody who listens to you. You cannot make progress without appropriate measurement, and this talk will illustrate this as well. Before I'm able to describe novometric, which in Latin means new measure, analysis, I must start at the beginning with optimal data analysis. It's called optimal data analysis because some company was trying to rip us off and we didn't want them to do it. It was originally called an optimal discriminant analysis. It doesn't matter, they're both ODA. And my discussion must rely on notes in the PDF that I prepared, which I hope you can access. Do you guys have the ability to access this PDF?
So for your kind information, so you can share the screen or I can share it on your behalf, the PDF with everyone.
I will try to share it on the screen. If that doesn't work, then let's do an alternative method. And there's some I can get by without the PDF, okay? Most I can get by without the PDF. So I'll begin by talking about an exploratory objective, an exploratory analysis. Climate change and was ruining the ability of people that survived on growing crops in Africa to live, and gully erosion specifically. And so they sought to identify individual and community-led adjustment measures, suggestions, things people could do that ensured continued habitation in their ancestral homes. They did not want to leave where their roots were. So they had individual and community-led was the class variable. The class variable is what we're trying to predict, okay, and is what we're comparing. And see, I thought you would have this. So since you aren't looking at this, I have to describe it. So
may I kindly share the PDF on behalf of you so that it can tell me which image it is?
The first exploratory, page 2.
Of course, so give me a moment.
Sorry, guys. It's hard to describe math without showing you some data. In fact, it's impossible. The next page, please. Donish, the next page. Yes. So you can see here, individual versus community-led adjustments in response. So the adjustment was use of ridges, shifting habitation, relocation, that means moving, and their house, and intensified cultivation, which means get as much as you can right now while you can. And so these were individual people that said what their motivation was. The red is going to be incorrectly classified. I'll explain that a little bit later. So when you do a chi-square for this, which is the traditional analysis, the only traditional analysis I'm going to report in this talk, it's 265. Now, the critical value to get P.05 is 7.82, and yet it got 265, which means all cells in this 4x2 table exceed this value. So the conclusion was everything matters, that the local population relies on individual and community-led adjustment measures to ensure habitation in ancestral homes. That's not very helpful. So instead, can we screen it up a little bit? Donish, the ODA model is the model which maximizes accuracy. And I'm going to describe what that is if adjustment is use of ridges or shifting habitation, then predict motivation equals community-led. And you can say we're under the column of community, it has these black numbers, 173 and 170. And those are the ones that this model predicts correctly, and it misclassifies the red ones, 85 and 65. On the other hand, if adjustment is relocation or intensified cultivation, then predict motivation equals individual led. So you can see under the individual led, it gets 172 and 45 correct in black, and it misses only 10 and 0. So it looks, just looking at these, at how the model performs, it looks like it does a lot better at the bottom two things than the top two things. So, well, how does it confuse? It's called a confusion table. It's pretty accurate. So you can see that the actual motivation is individual and community, but the predicted motivation is individual and community. You can see that it gets 59% of the individual motivation correct, and it gets 97% of the community intervention possible. So, well, what does this mean? If these are random numbers, what do you expect the correct amount of the sensitivity, the correct amount of accuracy to be? If you're rolling dice in the long run, 50%, it's equally probable. So, and each one of these should be 50%. If they're above 50%, you're doing better than chance would. In this case, community was 97.2 divided by 50 minus 1 time is 94.4% greater than chance, whereas individually motivated is only 18.2%. Better than adjusted for chance. Well, how do we summarize all of this? So instead of just talking about what percentage of accuracy we got, what was invented was a statistic called effect strength or sensitivity. What that is accuracy adjusted to remove the effect of chance. I don't want chance in here, so we're gonna filter all of that out. So ESS of 0 is the accuracy which is expected by chance. Roll it up a bit, please, to the second column, Donish. Up a bit. So here, yes, you can see ESS 0 is the accuracy expected by chance. Now, believe it or not, the University of Illinois gave me my own supercomputer, an IBM 3090 600 VF vector facility. And we used it. I tell you, we used it. It was unbelievable. I can't even estimate the amount. I know it was in the billions. I don't know how many billions of Monte Carlo experiments to study how well chance does in predicting stuff. And what we found out is that it seems funny, but I mean, and it's held up over 30 years, that ESS of, well, 0 is chance, that's what you expect. 25 is a relatively weak effect. 50 is a moderate effect. 75 is between 50 and 75 is a relatively strong effect. 90 is a strong effect, definitely a strong effect, and greater than 90 is a very strong effect. ESS of 100 means you get everything correct. You classify everything correctly. So in all the analyses that we're going to be talking about, ESS is a standardized index. And it just, what it does is it takes the accuracy of the model and it corrects it it removes the effect of chance. You can get an ESS of less than 0. That means worse than expected by chance. And the worst you can get is negative 100, which is absolutely impossible to get. I did not get a single negative 100 ESS in all those billions of Monte Carlo experiments, okay? So if you realize all conventional legacy statistical procedures that use confidence intervals assume the chance is 0. That is impossible. And you get absolutely everyone wrong. I did an experiment on this once. I would flip coins, and you know what? I got a side once. It landed on its side. It's not just on one. This 0 does not exist in the world, okay? It may exist in the universe. I'm sure it probably, yeah, it exists in the universe for sure, but not in this world, not yet. So in this case, ESS was, for this model, the ESS was 56.3, a relatively strong effect. It was resultant, I'm not going to say what the D statistic is, we'll explain that later. That was really profound change. And I'm going to move on because I took too much time on that. The second example, the next page, page 3, Danish, is confirmatory. The objective of this study was to discriminate right eye acuity based on left eye acuity. So the experimenters took the actual acuity measure and broke it up into 4 ordered categories. 4 was the worst vision, acuity less than or equal to the 25th percentile. That's a magic number, 25. Yeah, we're going to do that. And so the number 3 was acuity at the 50th percentile, equally magic. And the 3 was the acuity of, guess what, 75th. I mean, this is so uniform. So that's how eyes work, you know. I mean, what are they thinking? And you'll see you'll see why. And then of course the 4th was the best vision. And so you can see in the table there, the red are mistakes. Well, the ODA model says if it's to maximize ESS, if left eye acuity is equal to 1, then predict right eye acuity equals 1. Okay, and so forth. 2 is 2 and 3 is 3. And so you can see that it predicts the diagonal here. You can see also that down here at the bottom, scroll down, please, Danish. I'm sorry, guys. Yes, down further. Yes, so you can see for right eye acuity of 1, the sensitivity in predicting that was 77%, and which is the best of all of those. So the best vision was the easiest to predict the best. And 2, strangely, dipped down 67%, but if you drop confidence intervals around this, and we'll talk about that in a little while, then it's going to overlap. And 72% was next, but look at that, 62.4%. What I believe happened here is those are people with glaucoma or cataracts. I have both. This is cataract, that's glaucoma, and that's what leads to this error at the bottom. And if they were to actually, well, if they wasn't all compressed into that category 4, we would see a steep drop off, and they would know to eliminate those people from their sample to avoid that confound. And so now the problem is novometric analysis, you would use, in ODA, you would use the actual acuity number as opposed to break this up. Breaking up is notorious. It started with IBM scan sheets with the bubbles where you put in, I don't have 10 room for 10. So that was the 10-point Likert scales came from that. And then 7-point Likert scales came from that. It was computer guys who did this, not scientists, not measurement experts. And so, well, here's an example. Hi, can we scroll back up? Yes. So imagine 10 randomly selected attendees of an art auction volunteered information on whether or not they purchased an item. 1, I purchased it. 0, I did not. I always use 0 for no and 1 for yes, so I don't ever actually forget it. So if you look at this, it's like, hey, look at the zeros. They're all in a row, and it's ordered by age. So if you say, well, everybody who's to 33 and 35, take the middle of that. Everybody who's less than 34, say they didn't buy it, and everybody who's older than 34 did buy it. Excellent. 100%. And I'll read it to you. You don't have to scroll down. Keep this up here, please. It's the ODA model is if age is less than or equal to 34 years, then predict no purchase. Otherwise, predict a purchase. This model was statistically significant. P is 0.008. People 34 years of age or another were most likely to purchase an item. The ESS was 100. It's a perfect model. Correcting for chance, that's perfect. It's a perfect model. And well, I'll talk about the D statistic later. But now look at, you know, if they, so how many times have you seen this in every science? I mean, every single one of them, even physics, if you can believe it. They'll say, well, you know, I'm using logistic and it can't handle a bunch of categories and real numbers. Oh no. So what I'm going to do instead is I'm going to say everybody who's less than 30, I'm going to call them a 1. And everybody who's between 30 and less and 39, I'm going to call them a 2. And everybody who's between 40 and 49, I'm going to call them a 3. How about that? Happens all the time. Go look at the journals. Every single thing that you look at that's what they do. And so if you analyze that using ODA, it misclassified 2 people. You can see right there, the 31-year-old and the 33-year-old that are labeled as 2, it got it wrong. Because and this result was not statistically significant. P was less than 0.29 and ESS was 71.4, relatively strong, but with a small sample, that doesn't matter. You can't get them wrong when you have a small sample. There's no room for error. So if one recoded this, they'd say there's no effect. But and what's important to artists would be there is an effect, and they would want to know, pander to the people who are older than 34, because that's where you're going to get your money from. This happens all the time. This is one of the most significant problems in all of empirical science. Almost all of empirical science is contaminated by this. I'm sorry if I seem agitated. I am agitated. Maybe we skip to the next page, please. So that is the ODA models are the basic building block of everything here. But then it said, but how many studies only look at one variable? Studies look at a lot of variables. So now the way to handle that is with classification tree. And the first one that was invented was hierarchically optimal classification tree analysis, CTA. HOCTA is what we call it, because otherwise it gives you, your tongue gets bitten by your own teeth trying to say that too many times. At least mine does. And so the question was, we're taking this emergency department stuff, and what we're really interested in is getting the number of people who recommend higher, because that's where you advertise that. And so it's a Likert scale where 1 means, oh, I would never recommend it. 2 means I would probably not recommend it. 3 means, I don't know, 50-50. I'm on the fence. 4 means I probably recommend it. 5 is I definitely recommend it. So what we're going to try and discriminate in this example is people who are ambivalent, a 3, and we're going to figure out how to make them a 4, because that's the easiest change. It's hard to take a 1 or a 2 and make them into a 4, but a 3 isn't so hard. So the first step in developing any CTA model is to determine the minimum appropriate sample size. To make this discussion a lot, okay, I have to say this. There's only one time when the exact probability distribution for ODA is the same as the exact distribution for a legacy method. That legacy method is Fisher's exact test, and only when there's a binary measure. A 0-1 measure. So if you're getting a 0-1 class variable, I'm trying to predict two things, I'm trying to predict between 2 things, and I'm using a variable which has only 2 levels, that is the one time that these distributions converge, and I can't have any weights. And so what is that? Well, that's the worst, what do I call it? The worst case scenario is that I have the least precise measure, is the only one that's working. And so I'm looking to figure out statistical power, which means how many subjects do I need to run this study to be able to have a legitimate chance, a true chance of finding an effect. What's the worst possible case? Now, if the measurement of the variable that you're using to try and predict it is more sensitive, is a better measure, then guess what? Your power is greater. So rather than erring on the case of getting lucky, I'm predicting it on the basis of not getting lucky. Now there's a program written in R. My stuff is free, and it's my recompense to God. Is He gave me this. I'm giving it back to the world, and I'm not charging for it. And it will calculate this for you. And basically, I have it. Can you scroll it up a bit, Donish, a bit to the bottom of the page, a little further? Yes, so you can see here, just look at the 35. If you have 35 subjects in observations in each of the classes, you're going to get 97% if you only do one comparison power, 96% of 2, 96% for 3, and 93% for 4. 90% is the criterion for medical studies and for nuclear bomb studies and for things that are really difficult. 80% is good enough for most engineering stuff, at least first run engineering stuff. This is extremely powerful technique. In order to get this level of power using, for example, logistic, you have to have 10 to 20 times the number of observations. So the question was asked last time, what about small samples? Well, you can handle small samples. The trick comes with the confidence intervals, which we'll talk about a little bit later. So that's the first step, is figure out how many subjects do I need? Okay, so then you collect the data. The second step is identifying the original node, the root node. See where it says nurse attention there? That's a root node. And if you scroll up to the top again, please, Danish, please. And so how do you do that? Well, what you do is you do ODA, the univariate ODA we talked about first, and you do that on every variable separately. And what you do is you look for the one that has the highest ESS that is stable in jackknife analysis. We'll talk about that a little bit later too, but what that means is that it's probably cross-generalizable. And in this case, it was nurse attention. And I put less than or equal to 3 and greater than 3 because I'm an idiot. It should be 3 and 4, but whatever. It takes half an hour to change that. I couldn't do that. And so, but it's still less than or equal to 3 and greater than 3 is still true. So the first variable that entered into here was nurse attention. Then what you do is you go to the left side, and if everybody's correctly predicted over there, then you stop. You go to the right-hand side. But if it isn't, then you use every other variable, not the variables that you've already used that are in the pathway, because that'll give you a spurious answer that's useless. You have to use the different variables, and you look for the next one that has maximum ESS and is stable and is statistically significant. And you keep to grow this until you cannot grow any of the branches any further. Then you switch to the right-hand side and you do the same thing. Very laborious process. And so when you, so what you do is you use Zydac probability. Now Zydac I describe in my book, and it's other. So if you do one test, only one test, and you say the probability is going to be 0.05 is my criterion, is 0.05. But if you do 2 tests, it's no longer 0.05. You may say it's 0.05, but it's actually higher than that. So you have to have a lower probability so that when you do 2 of the tests, the cumulative probability remains 0.05. And there are 2 ways of doing this. One is called Dunn's procedure. She started from the right-hand side and worked it from the right. The other is called Zydac's. He started from left side and worked it towards the right. Dunn started right, worked left, and the other way for Zydac. And it turns out that Zydac is somewhat more powerful. Okay, he guessed right. And so everybody uses Zydac. And so, so what you do is after you get the fully developed model, then you start pruning it to remove the effects that are not really truly statistically significant. You can see here, the top one is less than 0.001, 0.003, those are no problem. 0.42 is very close to 0.5, but you always start with the lowest probability in the Zydac. So that 0.04 just barely squeaked in there. Now, the final step involves evaluating every possible model created by combining all different variations of structures on the left and structures on the right. There's an article on it. I have suggested readings that describe all of this stuff. And so can you scroll to the bottom, Danish, please? And so what that does is it finds the model, the tree model, which actually gives you the maximum ESS value, because the value of the ESS for the value for the first model, what was pruned for statistical significance, was 32. Now this model, the ESS is 35, and it uses fewer variables. They're exactly the same variables. It just chopped off the variable that was on the left-hand side. So that's how you do a hierarchically optimal classification tree. May we move to the next page, please, Danish? Yes, this is an exploratory analysis. It's exactly the same data set. This is an enumerated optimal, EO CTA. Instead of just looking at the first variable and then growing, you know, with the linearly, you know, what's the best, no, what's the second best, what's the third best, and so forth. Instead, what this thing does is it enumerates the first, the second, and the third nodes. I'll show you here. The first, the second, and the third. And the reason why we only do the top three is because it's computationally intensive. Danish, this is one application where quantum computing is going to come into to play, okay? And especially when you have things that are more than binary, okay? Well, we'll talk about that later. But so when you do this model, what it does is it looks for the highest DSS that it can get. And in this case, and it trims everything. And so we made an automated program to do this because it's so tedious. It took 2 to 3 days to do a big model of just working 10-hour days. It makes you go blind. It's silly, well, you know, and so we took over all of the mechanical stuff, but we made the mistake of calling it automated, which it is. It's automated. It's an automated mechanical analysis. But this was when machine learning was just coming out, and the old guard, the brilliant guys, the World War II generation said, we don't want it automated. We want to make sure that it's actually correct, because they didn't trust automation. Automation was horrible in World War II, and they won World War II by being fastidious. And so it was a mistake in language. I don't know what we could have called it instead of automated, because that's the word. But nevertheless, all it does is it just makes things simpler. The only thing that when we discovered this, and for the next 10 years, the only thing an operator had to decide was what was the minimum sample size for an endpoint. Minimum denominator, we called it. And so you'd figure out from your power analysis what it should be, and you'd say that. And so what the program would do is it would find the model that got maximum ESS using that minimum denominator or the next closest minimum denominator. Okay, that's it. And we didn't even occur to us to do anything else. This was all new. So using this, okay. So let's check this out. Patient kept informed about the treatment. Okay, cool. So if a patient is informed about what's going on with them, and the patient says that's at least 4, they like it, then you're going to predict that they're going to recommend it. 82% of the people are going to recommend it. So all you got to do to really boost up your recommendation is just keep your patient informed about what's going on. Don't ignore them. When they look like they're confused or upset, go up to them and tell them, here's what's happening. You know, update the amount of time you're going to have to wait. You know, and so that's like, wow, okay, thank you. And they don't get pissed off and they don't take it out on you. On the other hand, if you say, I'm ambivalent about that, man, I can't say good or bad. The next thing was concern for patient privacy. Interesting. Okay, so if you're ambivalent about being informed and you're ambivalent about privacy, only 41.4% predict 3 means I'm going to be ambivalent. So 59% are going to be ambivalent, which means only 41% are going to recommend you. That's terrible for business. On the other hand, if going through this tree model, if the patient is ambivalent about being informed, but on the other hand, they would recommend that you took their privacy pretty good. You were pretty private with them. You kept their privacy intact. The next thing, the final thing that pulled out was attention, how much attention they paid to you. Okay, and if you're ambivalent about that, it's 60% will still recommend you. It's more than the other one, 41%. It's still slightly more than that, and that's because at least you kept their privacy. But on the other hand, even if you don't inform them about treatment, if you show concern for their privacy, and if you pay attention to them, then 84% are going to be recommending you. The difference between 84% and 82% is very small. It won't even differ in a confidence interval examination. However, if you can't keep the patient informed, if it's too busy, like our ERs get sometimes, mass tragedy, like your ERs. Actually, India doesn't, guys are so inundated. No, this does not apply to the current situation. It applies to a normal situation. That even if you can't keep them informed, just guarantee their privacy and pay attention to them, which is when you have to guarantee their privacy, and you're going to make them happier than anything else. But it just takes more work. But if you can't. So anyways, and the staging table, forget that. I actually made a mistake on that, if you can believe it. I mean, what could go wrong when you're trying to say 70 years worth of work in 10 pages and in 4 days? Could you please go to the next page, please? So those are the basic building blocks, the bricks that you use for novometric theory. Now, from this point, skip 10 or 15 years of discovery and finally came upon novometric theory. This is an amazing thing, ladies and gentlemen. It's amazing. You'll see. The first axiom, and by the way, those of you who are physicists will recognize these axioms have parallels in quantum mechanics. This is tit for tat. And the first axiom is that it's statistically significant, but that's not enough. It's that you have an exact discrete confidence interval for the model, which is different, which lies outside of the corresponding interval for chance. And figuring out how to do that was a tremendous innovation. And because point estimates don't capture what happens. We want to know what 95% of the point estimates will be. And I just choose 95 because that's a tradition. And you have to honor the tradition of the people on whose shoulders you stand, you know, but you can do it for 99% or 97% or for 100% or for whatever you want. Okay, that's your choice. And it depends on the severity of the problem. If it's something like making sure your nuclear reactor doesn't become Fukushima, then you better use 100%. And if it's something like, I don't know what's not useful to do, but whatever it is, you can relax it if the standards, if the outcome of a disaster are not a disaster, if they're not significant. So axiom 1 is that the model and the chance have different confidence intervals. Axiom 2 is the structural decomposition analysis. What that means is to keep, sometimes imagine that you've got a whole bunch of variables and the variables have a really weak effect, but it's statistically significant at 0.05 for the thing. And you've got a ton of them and it's got to enumerate all those things. After 3 days, you'll get sick of it and you'll just turn off your computer and say, that sucks. I'm not going to do that. I'm going to do something else. And so, you know, and that this was, so we had to find a way, I had to figure out a way to make this go faster. And so in quantum mechanics, what one does is a principal component analysis. So, and they just take the first principal component. And what that does is it explains the majority of the variance. Okay, and so structural decomposition analysis is exactly analogous to principal components. And I love principal components. What principal components is actually just the partial derivatives of the variance covariance matrix. There are no assumptions required. It's a mathematical procedure. That's why physicists use it. And this is exactly analogous, except instead of maximizing variance, it maximizes accuracy. How beautiful is that? Okay, so, and we'll get into how that works. So we'll get into how that works. Well, no, I'll tell you how, I'm going to tell you how, I'll tell you how it works right now. So what it does is you do ODAs and you take your and you use the whole sample and you look at every single ODA and you find the model that maximizes your ESS and that is stable in jackknife analysis. And you say, okay, that's my first variable, and you take it out. And out of the data set, you remove all of the observations that variable correctly predicted because they're already correctly predicted. So what you're working with is the residuals, the things that were wrong, that you got wrong. And so then you look at every other variable, and you don't look at that variable because it's already in there, but you look at all the other variables and you use them all on that subset. And if there's one that's statistically significant at the at the Zydac value and it's still loose stable, then you pull that out. Now you got two variables, and you also pull out all the subjects that were correctly predicted by that. And then you go to the third step and you look at all the variables except for the first two, and you see which one has the highest ESS. It's got to be statistically significant by the first axiom, and then and so forth. And you know, you never go past about 4 variables. I don't care how big that sample is. The variables aren't measured that well. And these things are very powerful and reduces it very quickly. So So, and we'll show what that does a little later. Axiom 3 is that how you find the model, you know, because like one of the things that when reviewers, good reviewers do with statistical paper, with papers that use statistics, is say, okay, so you got this model. How do you know that it's correctly specified? And people don't even know what that means. And they just use jabberwocky to say, oh, because, you know, and the magic word that's used for handling that is, this is a robust statistical procedure. You know what robust means? Robust means is they don't know what they're talking about. That's what robust means. There's no such thing. If you make an assumption, if you build a house based on these assumptions and the assumptions are wrong, what happens to the house? It collapses, or the bridge, or anything else. The assumptions are crucial. Fortunately, ODA has no assumptions. That was one of the primary problems that we had to get rid of. And so, the way that you find, how do you know your model is properly specified? Well, there is a way in ODA, it's called Axiom 3. I keep forgetting, God, my names, you know, these cardiac arrests really ruined my names. I have troubles with names, even though I invented them. Minimum Denominator Search Algorithm, MDSA, of course. I've only read that 10,000 times. And so what this does is when you do your first CTA, your first automated CTA, you don't say what the minimum denominator is. You let the program figure it out, and then it figures it out, and if you bink, there's your first answer. If there's one, it'll find it. And then you say, how do I find the next one? Well, the answer to that, simple enough, is if the minimum denominator is 5, you change, you say, well, now the minimum denominator has to be at least 6. Okay, that doesn't mean that exists, a model exists, but it has to be bigger than 5. And so you run it again, and it comes up with another one. It says, here's the next best one. Minimum denominator is 15. Thank you, program. That's wonderful. Now do it again and make it 16 or bigger. And in this way, you keep going until the program says, no model can be found. And what this does is it finds every single statistically viable model that exists for your sample. Period. It's the only way. You cannot misidentify a model if you've got every single one of them there. That problem is now gone. Now, the fourth axiom is, well, training analysis is loads of fun, especially with the automated systems, but they take advantage of a chance. And so this is an important thing I'm doing. I'm not squandering my time. So I really want to make sure that this thing is going to hold up when it's used by other labs, or other labs check it out, try and replicate it, or when engineers take over and start to use it. And so the fourth axiom is validity of the model must be assessed using either cross-generalized, some sort of cross-generalized, but some sort of validational analysis. And there are a whole bunch of them. And I list K out of N, jackknife, split halves, one sample jackknife, multi-sample bootstraps, blah, blah, little jiffies, all sorts of stuff. In my book, I talk about that. In papers, I talk about that. But I use leave one out jackknife because that is the one that you can do with everything, okay? And here's how a LU works. You take, did I already describe that? I don't think I did. So I'm going to describe it just in case. So you have your sample. So what you do is you take your first guy, first observation, you hold it out right here. It's not, and I make a model based on 2 through N. And then what happens is I use that to classify number 1, and I put that classification result into a cross-class table. Now I got one observation done. You put number 1 back in, you take out number 2, you get a model based on 1 and 3 through N, you classify number 2, and you put it wherever it goes in the cross-class table. And you do this all the way through. And this way, the observations that are being classified were not included in the sample used to make the model. And it's like, rejoice, except that's a lower bound, I mean, that's an upper bound estimate for reproducibility, for cross-generalizability, because realize, for example, subjects 1 and 2, observations 1 and 2, they still share the data from observations 3 to N, okay? So there are much more profound ways of doing it, and I don't have time to talk about it now, but this is where measurement comes in. You must have, of course, you must know about measurement and about validity. And my book talks all about everything that you need to know for what I do, because I was pretty obsessive about it. So let's take an example. Now let's go to the next page. Let's go to that first, the first part. Yes. Okay, axiom 1. See, so it's ESS is 24%. Remember, 25% of us is relatively weak effect. Scroll down, please. Please scroll down. Now, down a little bit more. Yes. So what this diagram is, and this is also available. No, further up. I want to see the histogram. Thank you. Yeah, this program that does this is available for free. My brilliant colleague, Jim Rhodes, produced an R program that does this. I don't know how to run R, but I have to rely on him to do it, or maybe on some of you if you become colleagues. But nevertheless, this is how you do it. So what we do is we do a Monte Carlo resampling. So take your model. We have our data, all of our data. And what we do, we're going to resample that thing. So what we do is on step 1 is we go in and we randomly pick out one observation, we put it over here. And then we throw that observation back. We keep it over here, but we put it back in there. And then we do another random pick. And there's a chance that the same guy could be in there again. That's just the way it goes. That's what resampling does. And we get 50%. We continue to randomly pull observations out of that thing with putting them back in there until we get 50%. Why? Because it's been shown that 50% replacement bootstraps are the best possible representation of all possible bootstraps. Okay, so I want the most representative result. And I use 25,000 iterations. Why? Because computers are fast, and why not do it? In the old days, they used to do 500 something. Computers were much slower. And actually, on stuff that's important, I use 100,000. And I don't use more than 100,000 because on that same IBM computer, I studied how well these things converge and whether they converge to the known exact values. And at 100,000, you don't get much of it. You get a tiny, tiny bump if you do 25,000. But 25,000 is way better than anything less than 25,000. So I go with 25,000. If it's totally important, I go to 100,000. I don't squander resources by going more than 100,000 because it's never changed in billions of experiments. So I'm not going to bother with that. So now look at this diagram. You see the blue dotted line is the upper bound. So red is the model and blue is chance. Now the blue dotted line is on the red side. That means the upper bound, 95% bound of the chance is over there in the red distribution, and the red dots are on the blue. That means the 95% lower bound for the model is over there in chance, which means the 95% bounds for chance and for model overlap, which means it's not statistically significant by axiom 1. Now, I will point out something to you. The overwhelming majority, 90% or more of the effects that are published in legacy statistics, number 1, use 0 to compute to come up with the confidence interval, and they are all weak effects, which means that 90% or more of the research that has been published is saying things are significant that are not. Do you wonder why not one single Nobel Prize has been won using legacy statistics in any science? Now, there was one in economics that was using a log linear model, but that was a model of human behavior. It was not for statistical analysis. It was not inferential statistics. It was a model. The model worked well enough that it got a Nobel Prize. But other than that, it's all differential equations or quantum mechanics. Okay, so let's go to the moderate effect. So there's moderate effect, 48%. Please scroll up to the histogram. Yes. Now this is a moderate effect, almost a relatively strong effect. It would be we'll talk about that later. But you can see the red dotted lines are on the red side and the blue dotted lines are on the blue side, which means even though they interact a little bit, you can see the blue and the red stacking up there in the middle. The 95% lower bound for the model does not overlap the 95% upper bound for chance. So that is a statistically significant difference, okay? Now, please scroll to the bottom one. This is a relatively strong effect. And here you can see that these distributions don't even touch, okay? And you can see there's that -40. They got one that was almost not negative, negative like 35 or something like that. You're never gonna get -100. All right, so can we go to the next page, please? Axioms 2 and 3. Go down to the graph. Yes, right here. This is a little bit lower. I'll be a little bit higher. I need to see all the steps. Yes, that is MDSA. Now down, no. Down, just the numbers. I need to see the numbers. Yes, perfect. So I want to see, yes, the MDSA. This is every single model that exists you can read about it later. And for the study that we're talking about. So you can see there were 20 steps and step 20, it found no models. Strata's number of endpoints. At the first one, it found a strata with 12 and the minimum denominator was 5. You see that? And the ESS was 70%. Wow, that's a pretty strong model. And then in step number 2, so I said to the computer, minimum denominator is now 6. And it said, wow, now there's a 15. It's amazing that I actually remember those numbers from earlier. And then that was 69.2. It's not much worse. The ESS is not that much worse. And then it said, okay, well, the next one's 16. So it found a 20. This is every single statistical model that exists. You cannot get your statistical model wrong if you know what every single one is. And so there are ways to figure out which are the best models. So this is how you fail to misidentify your model. This is how you know that you pegged it. And oh yeah, I forgot to mention what the D statistic is. So I'll go back before. Sorry guys, I'm just trying to get this talk in. So when we talked about the CTA, this one had 3 variables and it got 32. This one had 2 variables and it got 35. This one had 3 variables and it got 37. But this is 3 variables. I mean, from 35, I'm going with 2 variables to only 2% more with an extra variable. Gosh, I'm increasing the number of variables 50% for a 2% gain in ESS. What is this? So I decided now ESS definitely corrects accuracy for chance. It removes the effect of chance. But now I got to deal with parsimony. Now the rules of science are, number 1, does it pass the stink test? If it sounds completely stupid, nobody can believe it, it's not going to work. Number 2 is, how accurate is your model in predicting phenomena? If it's accurate, then that's pretty impressive. But the third one is parsimony, Occam's razor. So I had the first 2 knocked. The third one I had to do, and that's where the D statistic came in. And I liked geometry a lot more than algebra. So I decided, I just sat down and said, that's it, I'm doing nothing else. I'm eating, I'm going to the bathroom, that's it. I'm just going to figure this out. I have to figure this out or I have to just quit and do something else. And so I did algebra. And I drew these pictures and I didn't realize yet what the pictures look like. And so I did algebra based on these pictures as Euclidean geometry, and I got confused, absolutely confused after 12 hours. Went to sleep, woke up the next day, said, okay, I'm doing algebra. I hate algebra. I'm going to do algebra instead. And I tried to do algebra. Guess what? Couldn't get it. Went to sleep, woke up the next day, did geometry, got it wrong. Tried everything I could think of, stuff I didn't even think of the first time because it didn't work. Like Einstein said, doing something again and expecting a different result is the definition of insanity. No, I'm not going that way. And so the 4th day, I said, this is it. I am either going to get this right or I'm going to quit. And I made a prayer. And believe it or not, I got it. It was really easy. And so what the D statistic does is it tells one how many. So say you've got a model and it has three attributes in it, 3 variables. And what D says is, how many more attributes do you need in a model that have the same mean amount of ESS associated with them before you get 100%? So look at that again, look at the moderately satisfied, the 12 attributes. That's 12 attributes are in this model. You can see the D there is 5.25 and you've already got 12, that's 17. But look at the bottom, you've got 2 and the D is only 1.55. That means you need fewer than you already have in your model to get a perfect answer. That is the globally optimal model. That is the number 1 model. You're not misspecifying, you're just taking the model that is the most accurate and most parsimonious, that satisfies the 3 rules of science. Okay, now, does that mean you disregard the S? No, because the D, the best D model, the lowest D tells you where you stand theoretically. If your D is low, it means you're close to the correct answer. You're close to E equals MC squared. If your D is high, that means you're way off. What else it tells you is all the variables that you used before are useless. You're not going to get the answer with those things. They had their big chance and they failed. So that you've got to do something else, either improve the measurement of the phenomena or think of other phenomena, explore other phenomena, go to exploratory analysis. But on the other hand, what these things, so that's what theoretical scientists want to work. But what engineers and clinicians and people like that want to use, they want to use the much more elaborate ones, because that tells you, based on current state of the information, what is my best chance of figuring out the odds that something's going to happen to this person and how to fix it. Okay. And so that is what is useful for precision medicine or for precision engineering. It's the best we can do with the current state of information. Now, what you do with this, and I haven't done yet, but I want to do with this, or maybe you guys can help me do this, is figure out how to make a calculator that so the physician or an engineer can say, well, I have this and this and this and this. And if those things are in there in a model, it's going to say, boop, here's the probability of success or failure. Okay, so this will be the most informative engineering or medicine tool ever developed, because it will take advantage of all known information and put it at your fingertips. On the other hand, for you theoretical types, you don't want to know that. You just want to know what really works, what works the best. And that's where you go to the other end of the spectrum. Now, to show you how this MDSA works, here's also, look, just keep the page right here, Donish, thank you. And see where it says, okay, so what I did in this next table is, the first thing was, what I did structural decomposition analysis. Instead of using 12 attributes, I only used 3 attributes, because I just look at the difference in time, 234 seconds versus 16 seconds, 133 seconds versus 10 seconds. Ha! So big advantage, and it gets much bigger as the thing gets, it becomes, it's not exponential, but it's parabolic. And the bigger the sample, the faster, the more time you save. Now look at the GO model. The GO model, globally optimal, lowest D was 1.55. It had 2 attributes and a minimum denominator of 769. Look at model number 6 over here. 1.55. See, I told you that it took me 4 years to try and invalidate this before I said, I give up. Okay, it always works. And so it found the globally optimal model. Now, the next model you find using MDSA is 3, and that was a 2.04. So look at here, that was model 17. So it missed model 18, because you see, it didn't have that extra attribute in there. So if you're an engineer, you really want to go without doing structural decomposition analysis. You want to do MDSA by itself if you can, because it's going to give you the most precision estimates, the widest variety of information that you can use. On the other hand, if you're a theoretical person, you're stuck with the easy, fast, fun ones to run. Okay, can we go to the next step? Next page, please. And go down to the table. Lower, no, next page. Yes, right there, perfect. Okay, so what this thing was, this is such a perfect, don't touch this, is exactly what I wanted, Donish. Bullseye. And so this was an experiment using 1 attribute, and that was gender. Yeah, no, it was cancer incidence. I was comparing cancer incidence from all sites by gender. And this is from SEER data set. This is what they do. They calculate this stuff. It's in America. It's a cancer deaths in America. And so it turns out that when I did the analysis, the minimum denominator selection algorithm, so I could find all 3 models. The first one that came out was a 6-strata model. It had 2 observations. What's the chance it's going to have a confidence interval that doesn't overlap chance? And it's not. And so I'll explain, okay, so I forgot to explain that confidence interval, but I'm going to finish this first. And so you can see the ESS was 33.2 and the D is 12. Wow, I had 6 already and it's going to take twice as many? That's horrible. And ESS, that's mine. So the next one was a 5-strata model. Look at the end, 63, and look at the ESS, 33.2. It's still got the same ESS, but it's still 10 and 5, it's still 15. It's not working well. And then I had 3, it was 31.9, so I got a little hit in ESS. It went from 33 to 32, but it's now they're only 9 total. See, 6.4 D, 6.4 additional effects plus the 3 effects that I had, that's 9.4. So it's not great, but it's better. And so of course, that means use the 3. And so here's a picture of the 3 cancer incidence. And you can see if it's less than or equal to 0.25%, because this is the number per 100,000. If it's less than or equal to 0.25%, that it's 53% males, 53% females. If they overlap, it's 50-50 males and females. You see this? 50%, 50. And so for the lowest cancer incidence, for the people that basically hardly ever get it, it's males and females are equal. But if you look at the middle one, which is 2%, it's 31% males, which means it's 69% females. It's mostly females. Females mostly get the intermediate level of cancer. And those who get more than that, it's 99% males. Hello, males get the cancer at a high rate. Females get it, and some males, debatably, but it's a joke, never mind that joke, get cancer, and then males and females are equal. So what does this mean? And the most challenging thing, how many studies look at males and females and compare them? Let's see, all of them. How many studies look at race and compare them? All of them, etc. How many times do you see researchers collecting simple, stupid, bureaucratic data, administrative data that are just like this, 2 levels or 3 levels, and compare them as if it's okay to do that? This is called Simpson's paradox, because no 2-strata model exists comparing all males versus all females. It doesn't exist. It's not, it's an incorrect specification. It's not robust. It doesn't exist. It's fantasy. Instead, what happens is that this exploratory comparison, males versus females, is statistically unmotivated. As I said, this is one of the most ubiquitous problems in all of empirical science. People are making comparisons as if it's their right. It's not their right. They have to figure out what comparisons are legitimate and which ones are not. Oh, I did explain the confidence intervals, right? You get the 95%, you throw them out. Oh yeah, and chance. Did I describe the confidence intervals? Somebody tell me, yes or no?
Yes,
Donish,
sir, you did.
I?
Yes, sir, you did while you were explaining the histograms.
It's my memory. And I'll tell you, if we have time and you want to hear about it, how I figured out what I don't remember. Can we go to the next page, please? So these problems are incredible, they're invisible, they're ubiquitous, and they're why research is not reproducible. 2 times already, the Congress of the United States has voted to cut funding for the National Science Foundation, and the National Institute of Mental Health, and the National Institute of Health, because the findings are not reproducible. And the reason they're not reproducible is because they are statistically unmotivated models. The models are not legitimate models. Now, this Novometrics will prevent that. It makes it impossible. Multivariable Novometric is the next thing. So let's just go to that. Perfect. That is perfect. So I'm going to read it to you. So what happened was this thing was done in multiple regression analysis. Have you ever heard of multiple regression? I hope you never do. You don't have to if you learn this stuff. If you do, well, just keep this in mind. So the question was, how do we figure out whether or not, what age affects? So there are all these things that you want to predict a person's age at which you're going to have to spend a lot of resources on them. This was like an insurance company or something like that. And so they did multiple regression. And to predict age, the formula was, and I'll just read it, it's in the notes, you'll see it. Age is equal to 42.55 plus 7.83 times the treatment condition dummy variable minus 1.82 times the female gender dummy variable minus 3.29 times the number of admissions, plus 0.51 times the number of hospitalization days, minus 1.4 times the number of ER visits, minus 0.06 times other procedures, plus 0.15 times laboratory tests, plus 0.27 times radiology visits, minus 0.15 times home visits, plus 0.11 times prescriptions, minus my favorite 0.0000064 times the cost. Yeah, that's it. Of course, it makes so much sense. Logical. Well, it was significant. P is less than 0.0001. We aren't going to discuss whether or not that model is legitimate or whether it's the most accurate or how accurate it is, but I did figure out how accurate it was. The ESS for this thing is 0.043. 0 is chance. This was 0.43 in training. I'm not about to try validity on this thing. It's a piece of junk. Time's too valuable to do that. So instead, I did a Novometric analysis. And it turns out that the only variable that stands up, the model, the globally optimal model is number of laboratory tests. And of course it was 0.001. I do that because that means not in our lifetime. And basically, I mean, because that's the convention, and more zeros is not impressive. Sometimes, just for jokes, I use the calculator that's also available free to compute. It's just a logarithmic. There are plenty of them, and I calculate the exact probability. Like it's 0.53 times 10 to the minus 37. Okay, so have fun with that. And so, but instead I use 0.0001 because I really don't want to upset people. So what this says is that 2.1% of the people, if they have 3 or fewer, 2.1% are older than 61 years. And look at that N, nice big fat N. And on the other hand, if the number of laboratory tests is 4 or bigger, 11.1% are there. So the ESS of this thing is, I'll read it, is 41.5. It's a relatively strong effect. T is 2.82. So to figure out the age exactly, you need 3 more of those bubbles, those round things, 3 more attributes to figure it out. So it's not a great model, but it is 96 times better than that multiple regression model, okay, with 1 variable, okay? So can we go to the final page, please? This is the future. Oh, it's beautiful. You can see the colors of my printout. You can't really see that. I can't see the colors. So the first one is multi-categorical class variables. Instead of just using binary variables, yes or no, you know, like, well, let's take 3. And so here, somebody published this thing in a ResearchGate, and I offered to do this analysis, and the guy like was old guardian, young kid, but he's in a place trapped by a bunch of guys who are like wed to it's sacrilegious to try anything new. This is 200 years old. How are we going to improve on that? Name anything else in science that's 200 years old that can't be improved on besides calculus. And so anyways, but nevertheless, so here in this diagram, you see a scatter plot, and it has 3 different classes. Forget what they are. It doesn't matter what they are. You got black dots and blue dots and red dots. How do you compare that with only 2 variables? Well, what you do is a Novometric model. And so the first variable there is X, and it says if it's greater than 10, and then it turns out 67% of them are class 3, and those are obviously the black dots. And then so, well, that's done. You can't build off of that. Then go, if it's less than or equal to 10, well, you use the variable Y. If it's greater than 10, say it's class 2, those are the red dots, and it gets 74% of them, no, 73% of them correct. And on the other hand, if it's less than 10, say that it's the other class, the blue class, and it gets 73% of them correct too. So the ESS of that is 56.7. It's a relatively strong model. You can't do this with any other analysis known to mankind. Multi-categorical. Nonish. This is where quantum computing comes in. This is incredibly, I don't know if it's exponential or parabolic. I haven't figured that out, and I haven't tried to. There's no reason, because I can't do it. But if you can figure out how, quantum computer guys can figure out algorithms to solve this problem in larger spaces for larger samples, we're going to be able to do stuff that no humans have ever been able to do. There are Nobel Prizes in this, folks. That's where you're going to get Nobel Prizes. This is how you're going to solve problems that can't be solved. Right there, that's one way. I'm going to show you a bunch more. Can we go squeeze to the next one? Okay, nonlinear phenomena. Now, just take a look at the and at the endpoints. On the leftmost, 60% were class 1. Okay, and it's significant 041, 001. Now, look at the one on the right. 50% were class 1, 50% were class 0, but still, I mean, it's 50 and 60. But look at the middle one. 0% were class 1. You know what that is? Do you know what that describes? A parabola. Now, parabolas are described mathematically. They're described in differential equations as well. But in real space, in real data, you can't really describe them. You can get a linear model or something, but that's not doing it. This is doing it. This found a parabola. You can also see how this same approach could be used to figure out a sine wave in the same way. Done it. This is quantum computing. The number of comparisons you have to do this is astronomical, even with only 3. Not astronomical, but it's horrible. Horrible. It takes a lot of concentration, dedication, and time to do it mechanically. So quantum computer could do this in moments. This is where, you see, the problem with using differential equations in quantum mechanics with normal data, as opposed to really small, fast-moving microscopic data, molecular data, atomic data, is that, wow, lost my train of thought. Oh yeah, that these data do not meet the assumptions of the quantum mechanical or relativistic assumptions. These things are not atoms. They don't behave like them. They don't look like them. They can't. The number, it's not a Hilbert space. It's not infinite. They're not real numbers. They're not real numbers. But this is how you do what you can do with calculus with non-real numbers, with ordinal numbers, even with categorical data. A calculus of categorical data. Okay, so that absolutely Nobel Prizes exist in this, in every field. So the next thing, ROC analysis, receiver operating characteristic used in radar. Now, what you do with that is you use, it's like a uniota. As a matter of fact, the most popular variation of figuring out area under the curve now, maximum area under the curve, is an ODA, a univariate ODA. But it doesn't allow weights. It doesn't give you exact discrete confidence interval for, can you see this? Can you guys see this? That's an ROC curve. And that 50% line, I draw a green band around it. That's because chance is not on that, exactly on that line. Instead, there's a confidence interval around it. And the red line, the curved line, that's the effect of the model. And you can see there's a confidence band around that too. And whenever the green and the red bands intersect, oh, that doesn't exist. And so instead of just having a point estimate, which is what ROC gives you, now you can do exact discrete confidence intervals as well to eliminate any ambiguity. And what about using multiple attributes? What about using a Novometric model or a CTA model to, instead of just one variable? Instead of trying to predict the phenomenon and seeing how it does against chance, why not use more information? Why not get a better ROC curve? So there are Nobel Prizes in this, obviously. Now, next, quantum computing. I've already talked about that, and I don't know that much about it. I mean, I love it, and I'm no computer guy. I'm not. But there's definitely, and discrete calculus. Okay, so let me go back up. Discrete calculus. Now, before I had my heart attacks, I actually was making progress on that, and I can't remember it, and my notes were. A lot of my notes were destroyed in an earthquake in San Diego. Okay, pictures, notes, music. Half my stuff was destroyed. And so what I wrote down last night, I'm just trying to think about it, and I gave it to Jim, and he has a friend who's an expert in calculus, and he needed more information. My memory is starting to come back, but parts of it, I'm working on it. I figured out a way to do that. I think that maybe the derivative is the cut points, the level in the descendant family. I think those are derivatives. The descendant family, when you do the MDSA, minimum denominator selection algorithm, I think those are derivatives, first derivative, second, third, fourth, et cetera, to however many there are. You can't keep going forever. There's a discrete number of them because they're not Hilbert numbers. And then I think that the integral corresponds to area under the curve, ESS, at that location. Just putting this out in the video in case some mathematician hears this and I'm correct. I mean, it's just a guess, okay, a best guess. I forgot. And go to the final thing, Markov models. One to the bottom page, please. Thank you. Now look at those two things. The first thing is symptom X, which is time, which is change in sleep as a function of pain. See, I'm so confused. I mean, and I did this. It's like, and it's just because of my memory problem. So change in sleep as a function of change in pain. Okay, so one of them is pain. That's the symptom X is pain. And symptom Y is sleep, quality of sleep. Now those graphs look like electricity on steroids. Not even lightning looks like that. How are you going to try and make sense of those squiggly lines? How are you going to try and predict them? Well, it's real simple. Use Novometric Markov analysis, where you say when symptom X happened, did it go down? And then you say, did symptom Y go up or down? But you weight both of these things by the change and you multiply it. I have papers that talk about this. They're free on this. You just type Markov in the search box and you find them. And look at this. This thing got 59% accuracy after adjusting for chance. 59%. D is 1.4. You need fewer than 2 more variables to figure out the relationship between sleep, to be able to predict your sleep. And the way people do this now, I know the person who did this actually, is they do a principal component and they take the variance and they try to, you can't do that with EEGs. This will work with EEGs, it'll work with temperature, it'll work with anything, with predicting earthquakes. You've seen the seismograph stuff. You don't think there are Nobel Prizes galore in this thing. There's a lot of data like this and nobody knows how to analyze it. And here's proof of how to analyze it simply using free software. And of course, your insights and discoveries. Danish, how much time have I used?
Not much, sir. It is almost an hour and 15 minutes, I believe.
And I was 75, perfect, because I tried twice it was 75 or 70 minutes, but I talked too much, it was 9 minutes. So I guess I can open it for questions now. Well, let me tell you, just to take 2 minutes. I was talking about this stuff, of course, on ResearchGate, and I love the French, man. Equality, liberty, fraternity. I mean, how beautiful is that, right? But also because they're not afraid to speak their minds. They prefer truth, über alles. And so the Frenchman was talking and people were listening on the ResearchGate, and he says, but Paul, what you're saying means that we have to reanalyze everything. I said, correct. Sadly, he was not willing to do that. Sadly. It reminds me of some parables from the Bible about people who were unwilling to do the right thing. So you don't have to start with the past. You can start with this. It won't take you much time. I've talked before about how to do it. It's simple. You go to my journal and you find simple little examples using one technique. You collect a data set of your own, or you find one in a journal or in a book or one of your colleagues, and you do the little analysis and you publish the little paper and you start figuring out how to publish a scientific article, and you send it to me and I help you. And then you've got an article in there. And then once you do that, I send you the CTA software for free, or you can pay me $5,000. Nobody ever has. And as soon as somebody does, I'm raising it to 10 grand because I don't want to sell it. This is my gift to humanity, but I need help. My journal needs help. I cannot get this thing indexed unless I have 70% of the people of the articles are not mine, okay? So I need help. And besides, it's a little homework assignment. What's the last time you ever got a publication for your homework assignment? And who cares whether it's indexed or not? This is it. I challenge you, try and beat an ODA model of any kind or Novometric. Try it. Good luck. You better live to be 1 billion and you're still gonna fail. So, because that's the way it is. You can get your data from the Freedom of Information Act. If you see a study that you like and it was funded by a government, you can get the data. If you can't, definitely can, okay? In fact, I hate to say it, but I got a great colleague right here. I never intend to lose him, even no matter where he goes, Praneeth. So, you know, and he's getting me, he's in charge of the data that we got a grant funded for. So you can get the data from journal articles and for books. Okay, all right, that's it. That's all I had. Now I'm ready for questions. Thank you.
So I'd like to tell
I
you.
hope that was okay.
Yes, so that was completely fine. And I'd like to tell you that how much grateful we are to you for such an informative session. So thank you so much for your time and effort, sir. And with this, I'd move forward with the Q&A session. I'd now like one of my anchors, Kushal, to lead the Q&A session. So you can post your questions in the Q&A chat box over there, and Kushal will lead the Q&A session.
Thank you, Sargun. First of all, I would like to extend my heartfelt thank you to Dr. Paul R. Yarnold for enlightening us. Hello, everyone. I am Kushal. Today, I will be leading the Q&A session. I already see some of you put your question in the chat box. Thank you for putting them in the chat box. Your question will be answered by Dr. Paul R. Yarnold himself. Sir, we have our first question. The question is, what is the scope of quantum mechanics for statistics?
Say that again slowly. Praneeth, I need your help. I can't.
Okay.
Gentlemen, tinnitus in both ears. It's
I will repeat it slowly, sir.
what is the scope of quantum mechanics?
What is the scope of quantum mechanics for statistics?
There is none. It's not a statistical, it's not used as a statistical procedure. But I didn't ever think that it would be either. I mean, it just was, I didn't. But then when I started to discover this Novometric thing, it wasn't like an aha or like I planned to do it, but it was like after I figured out the answer to a problem, I would summarize what it was. And then I found out that the axioms of quantum mechanics are analogous to the axioms of Novometrics, except quantum mechanics works with real numbers, and, well, Novometrics works with any numbers, including categorical and ordinal numbers. And so I'm not enough of an expert to do this. Now, I've asked one of our colleagues to be here. He's also Indian. He's a mathematician and works with mathematical physics, along with a Chinese genius and a Turkish genius and an Iranian genius. That was the thing that, I mean, it was waves. Their article was on waves, and that threw me out. And they were using differential equations. So you can also use quantum mechanics for that. So it's going to take a person like that to figure this out. Now, I asked a genius in Europe who retired, who has a PhD in math and a PhD in statistics, to help me with this, because I don't know enough math to do this. I don't know enough math to answer your question or even understand it. But he doesn't. I mean, he's retired and he doesn't have time. But he follows my work. So that's where this video is such a godsend, because hopefully somebody in some country, Russia's geniuses too. If all of the finest math and physics, I'm grateful, but our Chinese people lead authors in America. So just, I mean, I wish but they, no. So listen, this is not something that you do in your spare time. This is something you dedicate your life to. And it takes a genius to figure this out. I am at my limit. All I could do is what I have done. But to answer that question, to understand that question, it requires somebody who knows what I have done and also understands the incredible beauty of quantum mechanics. And I mean, the quantum computer guys, maybe one of those guys will do it. I can't. I'm sorry.
Thank you so much, sir. I hope it answered their question. So next question we have is the scope of ODA and Novometric theory for continuous data.
What's that? Can you repeat it?
Yeah. The scope of ODA and Novometric theory for continuous data.
Continuous
For
data.
continuous data.
Oh, yes.
Yeah.
Continuous data are the way to go. And like I said, most of the Nobel Prizes in early physics, at least, were based on finding how to measure phenomena correctly, precisely. And there have been multiple Nobel Prizes for finding more precise ways to do it, and in chemistry as well. And how has physics and chemistry performed compared to the rest of the sciences? No comparison. And that's because they can measure phenomena correctly. But in psychology, going to take undergraduate college students, write some questions and tell them to use a 5-point scale to say what you think. Is that physics? You're going to base your life on that going into space? Of course not. What is needed in every single field is correct measurement of correct phenomena. Novometrics will tell you what you know and how much you don't know. And it's the only thing that will tell you that. Nothing else will. And the best models use real number measures, real measures of real phenomena. Thank you.
Thank you, sir. So the next question is from Dr. Shakil. He's from Kashmir. His question is, which techniques or method will you recommend for handling the missing data values in Novometric analysis?
You know what missing data are? Missing. There's no way to handle that. You just gotta use the data that you have. And if you're missing data, that's going to make it really hard for that variable to be included in a model, unless you're willing to really dump the sample size of everything. Now, there's only one reason I would consider doing that, is if all the other measures separately and put together don't explain very much, but you have one that has missing data, but it explains it perfectly. And if the confidence intervals for that and chance don't overlap, then I would say you're finally on to something. So you begin with that variable. The variables have to battle it out. Novometrics will tell you how many models there are, where the variables enter, and so forth. And unfortunately, if you have missing data, that means that as you increase the minimum denominator, then that variable is going to drop out simply because it can't be represented. So you got to look at how that variable does when it competes with other variables with the same, where it has the same number of observations potentially can be compared. Or you can randomly sample out that number of observations from each variable and do bootstraps, do it many times and so forth, and compare them with comparable numbers of data. Okay. You also have to worry about whether the data are missing for some particular reason, which would be a confound. So missing data. In fact, I did a paper once I did a number of papers on small samples. They're in the ODA journal. And I remember somehow that one of them is called something about small sample analysis and the importance of assessing jackknife validity or Lou performance or something like that. The importance of doing reproducibility analysis, because the problem with small samples is that they don't necessarily reproduce. And I showed you that one where you take it and you measure it improperly. One is, is their age, and then the other is the age turned into 1s and 2s and 3s. And so that's a problem too. So small samples and missing data are a problem. Research is expensive. That's the way it goes. And whether or not a researcher is willing to invest the time and the energy and the resources that it takes to get a larger sample is a question of two things. Number one, how feasible that is, and number two, how motivated they are to get to the bottom of it. So that's a decision every investigator needs to make. Fortunately, Novometric theory guarantees that you can't get lucky and publish the lucky thing, which won't reproduce in other laboratories. Novometrics is the most challenging way to find an effect. And that's what I wanted. I wanted to protect science and to protect truth from falsehoods. So missing data are always a problem.
Thank you, sir. I hope it answered Dr. Shakil's question. We have next question is from Amit Kumar Mishra. He's asking, currently we have faulty quantum devices, NISQ devices. Is the trade-off of devices accuracy with traditional models accuracy worth it?
There was a difficulty in hearing to the question.
Okay.
Can you please?
So question is from Amit Kumar Mishra. I will repeat it. Currently we have faulty quantum devices, NISQ devices. Is the trade-off of devices accuracy with traditional models accuracy worth it?
No, I can't hear it.
We are not, this,
Can you type it, please? If
Sure, let
possible,
me
or
repeat
like maybe.
the question. So may I rephrase the question?
and he has good hearing.
So actually, Amit Kumar Mishra wants to ask that the current accuracy of quantum devices is not up to the mark. So is the
It's not
trade-off? Yeah. So is the trade-off between the traditional model, non-novometric models, with the device's accuracy worth it?
Would you rather make stupid mistakes that confound and foul up the world and are not reproducible, or would you rather get the correct answer? Would you rather treat your data with dignity or treat them like they are garbage? Is truth important or not? What trade-off? What is life for? I've dedicated my entire life for this. Twice I've given everything that I had to the church. I live in a slum. I don't do anything but research. Why? Because I want to use the gifts. I've eaten plenty of food. Plants and animals have died to support me. All the teachers who've helped me, my parents, my friends, the people who wrote the books, the people who made the materials I needed to do this. Why am I alive? What is my purpose? I have a gift. I am using that gift to my maximum possible capacity. Anything less than that is disrespecting everything and everybody that came before you. You cannot serve two masters. There is no shortcut to climbing a mountain. People who take shortcuts and get off the track end up in the bottom of glaciers. That's my attitude. Take it or leave it. I don't expect everybody to believe it, but those who are true scientists will understand, as I did, and Einstein did, and Newton did, and Edison did, that the joy is in the process. The joy is getting the answer correct, of being the first person in the world to understand the truth, and then spreading it to your fellow humans. That is the meaning of the life of a great scientist. And there's no shortcut. It's agonizing. I thank God that I have these gifts, but on the other hand, I don't fear death. It would be a relief, because I have to keep trudging forward. I love you all, don't get me wrong, but I'm not going to give you an incorrect answer if I can avoid it. Thank you.
Thank you so much, sir. I hope it answered the question. Audience, if you have any more questions, kindly write them in the chat box.
Don't be afraid. I just have a loud voice.
It's okay, sir. We understand. I think, sir, that's it. Thank you for this enlightening talk, sir. Thank you so much. Now I would like to hand over the event to Sargun. Sargun, continue.
Before moving forward, can we have the next slide? Yeah, right. So before moving forward, I'd like to tell everyone attending this session that if you want your certificates, in order to get your certificates, there's a QR code right in front of you. You can scan that QR code. And also, if you're not able to scan the QR code, there's a website name mentioned in the screen on your screens right now. You have to visit that website, and that's how you'll get your certificates. So moving forward, to end this session, I'd now like to request Danish, who's the event organizer, to present his thank you note to the guest and to everyone attending this session.
Thank you, Sargun. Am I audible?
Yes, you are.
So greetings, dear audience, and greetings, Dr. Yarnold. I hope all of you are in good health. So thank you for joining in, and I'm sure that you have enjoyed the event as much as I did. At HTS, we strive to bring informative sessions, workshops, and much more, hackathons and all. Now, respected Dr. Yarnold, I would like to extend a very warm thank you on behalf of all the audience that have been here and are here, and the HTS team. And it has been a wonderful and highly informative session, sir. And we had the privilege of listening to you talking about Novometric Theory, the work of your lifetime, as I remember you talking to me. And ODA, of course, or ODA, optimal data analysis. And I'm personally into quantum computing and statistics. I would say that I'm personally into machine learning, and I know how crucial all this is in terms of where we are going to be in next 10 years or next 5 years, and the kind of potential these technologies have: quantum mechanics, statistics, machine learning. So I would like to thank you, sir, for sparing your time from your busy schedule. I know how busy you are, how occupied you are with your research work, but still sparing time for us. We cannot thank you enough, sir. So kindly accept these words as a token of thanks from the audience and from us here at HTS. And we look forward to hosting many more events of topics which are not commonplace, which are alien to other people, and have the potential of being disruptive and revolutionary. Not today, maybe not tomorrow, but in next 10 to 15 years. So moreover, I will share the handouts with you, all the audience, via their emails. Thank you so much for joining us, and thank you, sir. It has been a privilege.
Let me say one thing. Speaking with you has been the greatest honor of my life. Thank you. Peace be with you. Namaste.
Thank you so much, sir. It means a lot. It means a lot.
You turn it off now?
Yeah, we can. Bye, guys.
So before
Stay
we can
safe.
say goodbyes, sir,
Be great. Be great.
Dr. Praneeth, before we
Yes.
can say goodbyes, there is a late question. I don't know. They asked it outside the Q&A session, so I would like you to answer it, because this might be a turning point for some people. So the question is very simple. It's, what was your motivation to enter into the statistical field? It is from Rajat Kumar.
I started college when I was 13, and I studied everything I thought I wanted to be. I mean, everything. And I got A's at first, and B's, and then I dropped out because it just wasn't for me. And I sat down with my mother and my father. My father was a statistician and my mother was a psychologist. And they said, will you ever graduate? And I said, I don't know, but there's one thing for sure. I will never be a psychologist and I will never be a statistician. So the answer is that I wasn't good enough to do anything else at a level at which I could be great, potentially great. And so I was lucky to find something which appealed to me and which I understood a lot of. With hard work, I could understand it, and with help from professors and different books and different courses. And it still took me a long time to find it. You see, this is the process of education, of learning, of professionalism. Being a scientist it's a journey. And you have to keep your eyes open and look at everything and listen to people and go to different talks. I would go and I would buy books at the book sales for the university where you pay 10 cents for a book. I would buy 100 books once a year on different subjects I knew nothing about, so I could look at them and see if there's anything of their interest. To find it out, you have to look, you have to search. It's an exploration. When you find out what you are good at, then you are on a straight research. You're on a track, you're on a racetrack. And what speed do you go? Pedal to the metal, baby. I'm gonna burn. You go as fast as you can, because you can never guarantee how long you're gonna live, or how long your professors will be there, or how long the university won't be flooded, etc. So that's how you find it out, by searching. This is why there are so few great scientists. There are so many people who could be great scientists, but they never find the racetrack. Or when they get on it, they don't put the pedal to the metal. They get some money and they start going in opposite directions. It's a question of what's inside of you. It's a question of you finding out how you are great. And most people, I believe, are great at something. I mean, look at the way the Japanese work. The older people are going away, but every single person in Japan, the horse shuckers, the engineers, the carpenters, everybody in the old Japanese took it as a matter of honor to be their best, to be a samurai of everything. The motto of the country was, we search the world for what is good and make it, and when we make it the best. That is how you become great. It's a mission, and you have to want it, and you have to be lucky to avoid disaster and diversion. That's how. It's just by searching and finding something that I was actually competent at doing and having people to help you. It's important to have people to help you. We are a community. Did that answer the question?
Of course, sir. So I believe in the same philosophy. I believe that looking in the wrong direction is as good as being blind. And people don't explore this themselves. So they don't know what they're good at. So as sir has told you, that explore yourself, find out what you're good at and do that thing. It might not be statistics. It may be something else. It may be literature, but do whatever you love. Thank you so much, sir. Thank you once again.
I love you guys. Peace be with you. Power forward. Thank you.
Thank you so much, sir. Thank you, Dr. Praneeth, for the logistics.
Thank you. Yeah.
Thank you,
Stay
Dr.
safe.
You too, sir. You too. Take care, sir. Have a good time.